Hello students, welcome to our second class on transportation problem. Today we will discuss on initial basic feasible solution of a transportation problem. Let us consider a transportation problem with M origins and N destinations. Here AI are the supplies, that is the availability at the origins, and BJs are the demands, that is the requirements of the destinations. In our previous lecture, we have discussed that the basic feasible solution of such kind of transportation problem will contain at most m plus n minus 1 positive variables, and the remaining variables are 0. Now, an initial basic feasible solution of the transportation problem can be obtained assigning allocations to different cells of the transportation table, which will satisfy the availabilities and the requirements. This kind of allocations can be done randomly or by following some specific rules. These rules are called methods. Today, we will learn 3 methods for finding initial basic feasible solution. Northwest corner method, least cost method, and Vogel approximation method. Let us start with northwest corner method. This method is the most systematic and easiest method for obtaining initial basic feasible solution. In this method, the basic variables are selected from the northwest corner cell of the table. That is, we start allocation from the northwest corner of the cell, northwest corner cell of the table. So, the name northwest corner method. Let us consider the following transportation problem. Here we see that there are 3 origins A, B and C and 3 destinations D, E and F. The availability at the origins, that is the capacities, are 50 units, 40 units and 60 units, a total of 150 units. And the requirements of the destinations are 20 units, 95 units and 35 units. Here also the sum is 150. So this is a balanced transportation problem. By northwest corner method, we allocate maximum unit allowable by the availability AI and the requirement BJ to the northwest corner cell. So let us start with 1 cell. In first row, we see that the availability is 50 units and the requirement of first destination is 20 units. So in this cell, we can allocate 20 units. So x11, the value of the decision variable x11 is equal to 20. Now we see that the requirement of destination D is fulfilled. So we cross over this, and the availability at the origin A, that is source A, is reduced by 30. Now we move on to the right of this cell and we allocate as much as possible in the 1, 2 cell. Here we see that the requirement availability is 30 units and requirement is 95 units. So we can allocate here only 30 units. And the value of the decision variable x12 is 30. And here we see that the availability at the origin A is exhausted and the requirement of the destination E is reduced to 65. Now we move downward and we allocate in the cell 2, 2. Here we see that the availability is 40 units and the requirement of this cell is 65 units. As the availability is 40 units, so we can allocate here maximum 40 units. So in 2, 2 cell we allocate 40 units and the value of the decision variable x22 equal to 40. Now we see that the availability of second source, that is the source B, is also exhausted. And the requirement of the destination E is reduced to 25 unit. Again we move downward and allocate to the cell 3, 2. Here the availability is 60 unit and the requirement is 25 unit. So we give here in this cell 25 units. That is x32 is equal to 25. And now the availability in this source reduced to 35 units and the requirement of this destination is exhausted. Now we move on to the right of this cell, that is to the cell 3, 3. Here we see that the availability is 35 units and the requirement is also 35 units. So we give here 35 units and the value of the decision variable x33 is 35. Now we see that allocation is done in 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 cells, and the number of rows, number of sources is 3 and number of destination is also 3. So the value of m plus n minus 1 is also is equal to 5. So the solution here we get is an initial basic feasible solution. Thus the final table is this: 2, 2 in the cell, 20 unit in the cell 1, 1, 30 unit in the cell 1, 2, 40 unit in the cell 2, 1, and 25 unit in the cell 3, 2, and 35 in the cell 3, 3. So the initial basic feasible solution is x11 equal to 20, x12 equal to 30, x13 equal to 0, x21 equal to 0, x22 equal to 40, x23 equal to 0, x31 equal to 0, x32 equal to 25 and x33 equal to 35, and the corresponding transportation cost is rupees 1015. So we get the initial basic feasible solution as this. So we have learned to find the initial basic feasible solution using northwest corner method. Our next method is least cost method. This method is also known as matrix minima method. In this method, we will first choose the cell with minimum cost in the cost matrix and allocate as much as possible in the cell. Then we discard the row or the column whose capacity or requirement is exhausted or met. Now, after adjusting the requirements and the availability, the process is repeated with the reduced matrix. Let us consider the transportation problem with 3 sources and 4 destinations. Here, AIs are the availabilities at the sources and bj's are the requirements of the destinations. We see that the sum of the availabilities is 90. Also, the sum of the requirements is also 19. So, this is a balanced problem. First, we see that in the cost matrix at the cell 2, 4, the cost is minimum. So, we will allocate in this cell as much as possible from the availability and the requirement. Here we see that the availability at the origin B is 37 unit and the requirement of the destination G is 25 unit. So we can allocate 25 unit in this cell, and therefore the value of the decision variable 2, 4 is 25. Now we see that the requirement of this destination is met and the availability at the source B is reduced to 12. So we discard the destination G and we get the reduced matrix in this way. Here we have 3 sources and 3 destinations. Now, in the cost matrix, we see that minimum cost occurs at 2 cells. In the cell, minimum cost is 3 and it is in the cell 1, 2, also in the cell 3, 1. We arbitrarily choose one of these cells for allocation. Let us choose the cell 2, 1. Here we see that the availability is 19 and the requirement is 18. So we can allocate 18 unit in this cell. And the value of the decision variable 1, 2, x1, 2 is 18. We see that the requirement of the destination E is fulfilled and the availability at the source A is reduced by 1. So, the requirement of the source destination E is exhausted. So, we discard the column E and we get the reduced matrix. We get the reduced matrix as with 3 sources and 2 destinations. Again, examining the cost matrix, we see that the minimum cost occurs in the cell 3, 1 and maximum possible allocation can be made in this cell is 16 unit, which is the minimum of the availability and requirement. And the value of the decision variable x31 is 16. Here again the requirement of the destination D is fulfilled and the availability in the source C is reduced to 18. So we discard the destination D and the reduced matrix is this. Here there is only one destination and 3 sources and the availability at the sources are 1, 12 and 18 and the requirement of the destination F is 31, which is the sum of these availabilities. So we allocate 1 unit in the cell AF, that is 1, 3. In the cell we allocate 12 unit in the cell 2, 2, 2, 3 and we allocate 18 unit in the cell 3, 3. That is 1 in the cell 1, 3, and the value of the decision variable x13 is equal to 1. Allocate 12 unit in the cell 2, 3, and the value of the decision variable 2, 3 is 12, and allocate 18 unit in the cell 3, 3, and the value of the decision variable x33 is 18, and all the requirements and availabilities are fulfilled. Here the number of allocation is 1, 2, 3, 4, 5, 6, and we have 3 rows and 4 destination. So the value of m plus n minus 1 is also 6. So the solution is a basic feasible solution, and we say that this is the basic feasible solution of the given transportation problem, and the solution is x12 is 18, x13 is 1, x23 is 12, x24 is 25, x31 is 16, x33 is 18, and other decision variables have the value 0, and the corresponding cost is rupees 377. So this is the solution obtained. This is the initial basic feasible solution obtained by the method least cost method or matrix minima method. Let us discuss another method of finding initial basic feasible solution. This method is known as Vogel approximation method. This is also known as unit penalty method. Here we calculate the penalty for each column and each row of the cost matrix. The penalty is the non-negative difference between the minimum and the next minimum costs in each row and column. Let us start with an example. Consider the following transportation problem. Here there are 3 sources and 4 destinations. AIs are the availability at the sources and BJ are the requirements of the destinations. Here we see that sum of the availabilities is equal to the sum of the requirements. So the given problem is a balanced transportation problem. Let us calculate the penalties for each row and each column. Here we see in the first row the minimum cost is 2. And the next minimum cost is 3. So the penalty for the first row is 1, and we write it within the bracket against first row. Similarly, the penalty for the second row is 3 and the penalty for the third row is 1. Now we calculate the penalties for the columns. In the first column, we see that the minimum cost is 3 and the next minimum cost is 4. So the penalty is 1. For the second row, again the penalty is 1. Also for the third row, the penalty is 1. And for the fourth row, the penalty is also 1. Now we have to identify the row or the column which has maximum penalty, that is largest penalty. We see that 3 is the largest penalty and it is occurred in row 2. So we select this row for allocation. Now we allocate as much as possible in the cell with least cost in this row. We see that 1 is the least cost in this row and it occurs in the cell 2, 4. So we allocate as much as possible in this cell. Here we see that availability is 37 and requirement is 25.
So we can allocate 25 units in this cell, and the value of the decision variable x24 is 25. Now we see that the requirement of column 4 is exhausted. So we discard this column and adjust the availability of source B. Now the source B has the availability 12 units. After discarding this column, we get the next matrix. Here we again calculate the penalties for each rows and each column. The penalties are 2 for the first row, 3 for the second row, 1 for the third row, and penalties for the columns are each 1. Now the maximum penalty, that is largest penalty, occurs in the second row. And in the second row, the cell 2-1 has minimum cost. So we allocate the minimum of requirements and availability in this cell, and that is 12 unit. So x21 is equal to 12. Now we see that the availability of the destination of the source B is exhausted. So we discard row 2 and we adjust the requirement of the column 1. Now the requirement of the column 1 is 4 unit. After discarding source 2, we have with this cost matrix. Again we calculate the penalties of the for each row and for each column. Here we see that a tie is occurred. Maximum penalty is in the first row and also in the first column. So we break the tie arbitrarily. We can choose either the first column or the first row. Let us choose the first column. Here let us choose the first row. Here the minimum cost occurs in this cell, that is in the cell 1, 2. So we allocate as much as possible in this cell. We see that we can allocate 18 units in this cell. So the value of x12 is 18, and we see that the requirement of the second column is met. So we discard this column and we adjust the availability in the source A. Now the availability in the source A is 1 unit. After discarding this column, we get this cost matrix. Again we calculate, this cost matrix has 2 rows and 2 columns. Again we calculate the penalties for each row and each column. The penalties are 1, 4, 2 and 1 respectively, and the maximum penalty occurs in this row. So we allocate in this row. Here we see that minimum cost occurs in the cell 3-1 CD, that means 3-1, and so we allocate here. We can allocate unit 4 in this cell, as 4 is the minimum of availability and requirement. And the value of the decision variable x31 is 4. Now the requirement of destination D has met. So we discard the destination D and we adjust the availability in the row C. Now the availability in the source C is 30 units. After discarding first column, we get only 1 column and 2 rows. So and see that the sum of the availability is 31 and the requirement of this row, this column is 31. So we allocate 1 unit in AF cell and 30 unit in the CF cell. So the value of the decision variable x31 is 1 and the value of the decision variable 33 is 30, and ultimately all the availabilities and the requirements are fulfilled. Now we see that number of decision variables with non-zero values are 1, 2, 3, 4, 5, 6, and the number of rows in the given transportation table is 3 and number of columns is 4. So the value of m plus n minus 1 is 6, which is equal to the number of allocations. So this solution is an initial basic feasible solution of the given problem, and we obtain this solution using Vogel approximation method. So the solution is x21 equal to 18, x12 equal to 18, x13 equal to 1, x21 equal to 12, x24 equal to 25, x31 equal to 4, x33 equal to 30, and the values of the other decision variables are 0, and the value of the corresponding transportation cost is rupees 355. So this is the Vogel approximation method. Today we have discussed 3 methods for finding initial basic feasible solution of a transportation problem. In our next lecture, we shall learn how to find the optimal solution of a transportation problem. That's all for today. Thank you.